Imagine a single experiment so profound that it shattered centuries of assumptions, rewrote the rules of science, and set humanity on a new path of discovery. Picture a moment when the invisible became visible, when the universe revealed a secret so fundamental that nothing in physics would ever be the same. This isn't just a story about test tubes and chalkboards. It's about curiosity, courage, and the relentless human drive to understand the world. Today we're diving into the physics experiment that changed everything, the double-slit experiment. To appreciate why this experiment is so revolutionary, let's rewind to the early 1800s. At that time, scientists were locked in a fierce debate. What is light? Some believed light was made of particles, tiny bullets shooting through space. Others argued it was a wave, like ripples on a pond. Isaac Newton, the giant of physics, was firmly in the particle camp. But a new generation of thinkers was about to challenge that view. Enter Thomas Young, an English polymath with a knack for asking the right questions. In 1801, Young set up a simple but ingenious experiment. He shone a beam of light at a barrier with two narrow slits, then observed the pattern of light that appeared on a screen behind the barrier. If light were made of particles, you'd expect to see two bright spots, one behind each slit, where the particles pass through. But that's not what Young saw. Instead, he observed a series of bright and dark bands, an interference pattern. This was the unmistakable signature of a wave. When waves pass through two slits, they spread out and overlap, creating regions where the waves reinforce each other, bright bands, and regions where they cancel out, dark bands. Young's experiment was simple, but its implications were enormous. It showed that light behaves like a wave, not a particle. This was a direct challenge to Newton, and a turning point in the history of science. But the story doesn't end there. Over the next century, scientists built on Young's work, developing the wave theory of light and uncovering the mysteries of electromagnetism. James Clerk Maxwell's equations unified electricity, magnetism, and light, showing that light is an electromagnetic wave. The wave theory seemed complete until the early 20th century, when a new set of mysteries emerged. Enter quantum mechanics. In 1905, Albert Einstein explained the photoelectric effect by proposing that light sometimes behaves like a particle, a photon, with discrete packets of energy. Suddenly, the old debate was back. Is light a wave or a particle? The answer, as it turned out, was both and neither. The double-slit experiment would become the stage for this new drama. Let's fast forward to the 1920s. Scientists now had the tools to perform the double-slit experiment, not just with light, but with electrons, atoms, and even molecules. What they found was astonishing. When electrons are fired one at a time through the double slits, they don't just form two piles behind the slits as you'd expect if they were particles. Instead, over time, they build up the same interference pattern seen with light. Each electron seems to interfere with itself as if it's traveling through both slits at once. But here's where things get truly strange. If you try to observe which slit the electron goes through by placing a detector at the slits, the interference pattern disappears. The electrons behave like particles again, forming two piles instead of an interference pattern. It's as if the act of measurement forces the electron to choose a path, collapsing its wave-like behavior into particle-like behavior. This is the heart of quantum mechanics. The outcome depends on whether you look. This result is so counterintuitive that even the greatest minds in physics struggled to make sense of it. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger debated what it all meant. Was reality fundamentally indeterminate? Did observation create reality, or was there some hidden mechanism we hadn't discovered yet? The double-slit experiment became the ultimate test of quantum weirdness, a window into a world where particles can be in multiple places at once, and where the act of looking changes what you see. But why does this experiment matter so much? Because it reveals that the universe is not what it seems. At the quantum level, reality is governed by probabilities, not certainties. Particles don't have definite positions or paths until they're measured. The double-slit experiment shows us that the act of observation is not just passive, it's an active part of the story. This challenges our deepest assumptions about objectivity, causality, and the nature of reality itself.